Okay, let me pull up the worksheet I have. Right, okay, so let's see, plan. One, you have a midterm tomorrow. So I thought today we should go over some last material that was covered on Thursday, so we're all on the same page, and then after we can maybe do some review. So today I want to talk about orthogonal matrices. I want to talk about maybe some projections. And there's not too much there. And then any review you guys want to talk about. And this will kind of be up to you. I have nothing planned on the review side, so you're welcome to ask me questions. Remember, I do have office hours today. My usual time, 3:30. Okay. So why don't we start with orthogonal matrices. Okay, so let's just start with a definition. That's a good way to start with any new concept. So we let U be an n by n matrix. We say that U is orthogonal if, and only if, what is the definition of an orthogonal matrix? If, well, its columns are orthonormal. And because it's an n by n matrix, that's one way to say this is that U transpose U equals the identity, and which implies, since it's square, that U transpose equals the identity. So one thing to stress is that this must be a square matrix. A matrix can't be orthogonal if it's not square. Just like a matrix can't be invertible if it's not square. And the second thing to note is that when we say, if we kind of look at U transpose U, you just write that out. If U has columns, let's say U1 through UN, which means in the transpose it has rows U1 through UN. If this equals the identity matrix, then if you just kind of break this apart, you see that, for example, this first entry here is exactly the dot product of U1 with itself. And the second entry, maybe right below it, which is a 0, is the dot product of U1 with U2. And so what this is saying for an orthogonal matrix is that the columns of U are orthonormal. So we went over this a little bit, but just to warm up, or maybe recall. So it's pretty easy to get this confused because we call this an orthogonal matrix, even though the columns are orthonormal. And so that's mainly for historical reasons. So, just one thing to not get confused by. And another thing that's often confusing is that we can call a matrix orthogonal, and we can also call vectors orthogonal. And in this class, we've tried to stress like the differences in vocabulary between different objects. For example, like vectors can be linearly independent, but a matrix can't be linearly independent. But in this case, orthogonal can apply to both a collection of vectors and a matrix, but they mean different things. A collection of vectors is orthogonal if their dot products are all 0. A matrix is orthogonal if it's square and its columns are all orthonormal. Another thing to note is that U transpose is the inverse. Okay, so this is what an orthogonal matrix is. And you might wonder why these are important. So what's so important about them? Or what do they mean? Well, the first thing, if you want to understand an object, maybe list some properties about it. So let's let U be an orthogonal matrix. And we'll let X, Y be an R, N. It is an N by N matrix. Then we went over this a little in the last section. You have some nice properties. The norm of UX is the same as the norm of X. And UX dot UI equals X dot Y. Okay, and how do we prove this? Well, we kind of proved it also last section as well. I'll just go over that again. Right, so the first one is implied by the second one. Right, if you take Y to be X, then this X dot X is the norm of X squared, and this is the norm of UX squared, and so you get that. Taking square roots, you get the first one. So it just needs to prove the second one, and that's just unwrapping the definition of dot product. Right, dot product of two vectors, you take the transpose to the first one, and then inside here is the identity. This is just X dot Y. Okay. So, I mean, this is nice. You have a proposition that tells us a little about orthogonal matrices, but like, what does this really mean, right? I mean, this is saying, what is this first one saying? It's saying that if we kind of think about U as the linear transformation, like X goes to UX, it means this linear transformation, X going to UX, doesn't change lengths. Right? And so it, this linear transformation may take a vector, some other vector, but it doesn't scale it at all. Okay, and what does this one say? It says if you have two vectors, then it doesn't change their angle between them. Right, so you're kind of piecing together a picture in your mind, right? If you have some collection of vectors, maybe x1, x2, x3, then you apply U to it, it shouldn't change their lengths and also shouldn't change their angles. So you just get some kind of rotated picture almost. Right? All the angles are the same and all the lengths are the same. Right? Or actually there's something else it could do. Instead of just rotating, it could maybe reflect a vector, as long as the angles are still the same. Right? So it could rotate as a bad drawing of a reflection or reflect. There's a question, can we think of U as a change of basis matrix? I mean, I guess you can think of any invertible matrix as a change of basis matrix. In that, it's an invertible matrix, and so its columns form a basis for Rn. And so if you want, you can think about that as a change of basis. But here, I guess we're just thinking about it as just some linear transformation. But to go on that, so what if, so, we're thinking of U as just any sort of linear transformation, which is really, because of these properties, is just some rotation or reflection. And this is actually true in general. For any orthogonal matrix, it must be a rotation or reflection, something like this. But there's something else we can look at, which is the matrix U transpose. And that will be something we're familiar with change of bases and projections. Why does the second property imply U doesn't change angles? Oh, right, because if we go back to what dot product really means geometrically, it's kind of giving you a notion of angle. So this is way back, maybe 3 weeks ago or so. The dot product of two vectors lets you define what it means to have an angle between two vectors, because at least in R2, we have this equality where theta is this angle between the two vectors. So at least in R2, this is what this is true. And so this lets you actually in Rn define what it means that what the angle between two vectors is. And so that's what we mean when their dot products are preserved. It means, since their lengths are also preserved, that this angle must be preserved. And that's why it kind of doesn't change angles. So intuitively, dot product gives you a notion of angle. Okay, so let's look at another example. So let's look at U transpose and U transpose U. All right, let's say that U has orthonormal columns. But not necessarily square. So it just has orthonormal columns. Okay, and let's look at U transpose X and U transpose UX and see what these are equal to. Okay, so let's do the second one. Might be easier. Let's look at this. So let's say U is not square. I'm going to draw it maybe as a not square matrix so we don't get confused. We have columns U1 through UN. Here's U, here's U transpose. You have rows U1 through UN. Right, what should this equal? Well, this actually, I mean, by the same reasoning we had before, this is still the identity matrix, right? You have U1.U1 as the top left entry, that's still 1, and you have U2.U1, that's still 0. So this is actually still just X. U transpose UX is still just X. But what about this one on the top? Let's do U1, UN, here's U, and then U transpose. And then we have X. Okay, let's just like piece this apart. So this is no longer like the way matrices multiply. This isn't this matrix you get on the left side. U transpose is not the identity matrix because you're not getting U1.U1 anymore. But if we just kind of write this out, we get U1 through UN, and then what do we get over here? We get a matrix whose first entry over here right? It's just the way we multiply is U1.x, x.U1. And the second entry is x.U2. The last entry, x.U1. Right? And then if we just keep multiplying this matrix, here's U, here's the U transpose X. Right? Now we have this first entry times U1 plus the second entry times U2. So writing this all out, this equals, let's see if I can, oops. This equals x dot u1 times u1 plus dot 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 x dot un times un. And what is this? Holding. Oh no. All right, I'll just square this off. And what is this whole thing? This is equal to the projection of x onto the column space of u, right? This is exactly, you're projecting onto u1, and because u1 is orthonormal, u1 dot u1 is 1, so you don't need to divide by that. And so this is exactly the projection, right? And so to sum up, we have u transpose x equals the projection onto the column space of u of x, and u transpose ux equals x, right? And if u is square, then if u is square, u square, then both of these are equal to the identity matrix. Well, this is always equal to the identity matrix, but this top one's equal to the identity matrix if u is square. And what we're saying is that should equal the projection onto the column space of u. Well, it does, because the column space of u, since u is square, you have n linearly independent, n orthogonal vectors, which are then linearly independent in Rn. So the columns of u are a basis for Rn. So if you're projecting a vector onto just Rn, you should just get the vector itself, x. So this kind of makes sense. So yeah, that's just kind of the main takeaways of orthogonal matrices for us is that as a linear transformation, they don't change your angles or your lengths. And if you take an orthogonal matrix, then you form u transpose. This gives you what's called a projection matrix. So definition, if u has orthonormal columns, we call the matrix u transpose a projection matrix. Because it projects into the column space of u. Okay. What do you think? Some questions. Maybe I'll say, well, first let's just show p squared equals p. Here's the first warm up. And then the second question is, what do you think are the eigenvalues and eigenvectors of p? So why don't everyone work on some of these for a minute or so. Show p squared equals p. This one's not too bad. And then try to think about what the eigenvalues and eigenvectors are. Think about this intuitively first. Intuitively. And then if you want, well, I haven't given you any entries in here, so you can't actually find them explicitly. So just in general, intuitively. What do people think are the eigenvalues and eigenvectors of P? One and zero was suggested. Would the eigenvalue just be one and the eigenvector just Rn, R to the n? Yeah, so both of those are, you do have an eigenvalue of one and you also have an eigenvalue of zero. And the eigenvectors are not just, there's more than just a single eigenvalue, so we should separate the eigenvectors, right? And the way to think about this is you have some subspace. This subspace is exactly the column space of U. And what P does is it projects onto the column space of U. And so it takes any vector and P gives you the projection. So this is PV. Right? And so what vectors are kind of special to this projection matrix? What are scaled by some, scalar? Well, if you take V to be exactly perpendicular to the column space of U, if V is in the space that is perpendicular to the column space of U, so if it's in the orthogonal complement, then PV equals 0. Right? Which means exactly that 0 is an eigenvalue, and the eigenspace is exactly all the vectors in the orthogonal complement to the column space. Right? Okay, and then there's another vector that is scaled by just something, which is, what if you take V to be in the column space already? Does this mean P is not invertible? Yeah, exactly. Right? Because if you project, right, how do you undo that? Right? How do you undo projection? Well, you can't, because you don't know what was, there's many vectors that project to the same vector. And so it's not invertible, right? Because 0 is an eigenvalue. Well, there is a case where it is invertible, which is if this is empty, if the orthogonal complement to the column space of U is empty, which means, what if the column space of U was all of Rn? If this was all of Rn, which means that, exactly that the columns are linearly independent and they span, then 0 is not an eigenvalue because there is nothing in here. And so P would be invertible. And that's just in the case where, if the column space of U is all of Rn, that means exactly that U is a square matrix. It means U is an orthogonal matrix. And this is invertible if U is orthogonal, because U orthogonal implies U is invertible. And so you can just take the inverse of that. If U is orthogonal, then this is just the identity matrix. So, yeah. And anyway, yeah, continuing, if V is in the column space of U, then PV just equals V, which just implies 1 is an eigenvalue, and the eigenspace is column space of U. Okay, and so then the next question is P diagonalizable? We know in general it's not invertible, but we also know that invertibility and diagonalizability have nothing to do with each other. So what do you think? Is P diagonalizable? Any guesses? Yeah. Guess number one is yes, question mark? Yeah. P is diagonalizable. Right? Because you have two eigenvalues, but that doesn't matter because if you want to check diagonalizability, you need to check whether the eigenspaces, um, are all of Rn. You need to check if there's n linearly independent eigenvectors. So you take your eigenspaces and do these collectively, if you add them up, give you all of Rn. Right? And yeah, exactly. They do. The column space of U perp plus the column space of U, those two spaces together span all of Rn. Because column space of U perp and column space of U span, they both collectively span Rn. So you have eigenvectors, some from here and some from here, and they span Rn. Exactly. Related question from a practice. So we have a question. You have a subspace of Rn, and let P be the n by matrix. Okay, let's write this down. So there's a question, which is you have W, a subspace of Rn. P is the projection to W. So it's the n by n matrix of the orthogonal projection onto W. Okay. Then every column of P is an element of W. Okay. What does it mean to be an element of W? It just means like a column of P is a vector in Rn. W is a subspace, so is that vector inside W? Right. So here P equals, if it's the n by n matrix of orthogonal projection onto W, that means it's U transpose, where U has equals some matrix, and U1 through UN, maybe not N, but D, we'll say, is an orthonormal basis for W. Okay, well, so normally this would be, this is an N by D matrix. But it's saying, oh yeah, okay. So P equals U transpose, which is a D by D matrix. But it's saying that it's actually N by N, which means that seems to mean that W has dimension N. So it seems to say true because W would have to be Rn, unless these are different N's. But the way it's written, I would say True, because this would imply D equals N. Oh, this is elements. Element of W. Yeah, so this is what it means. So when we say matrix of orthogonal projection onto W, we mean this matrix, right? Because this means, so the orthogonal projection is a linear transformation. And so we're just taking the matrix of that linear transformation. Right? It's the transformation which sends a vector V to the orthogonal projection onto W of V. And what is this matrix? Well, it's given by U transpose, because we just said that this matrix projects onto column space of U. So if we just make U have column space equal to W, then this will project onto W. Okay. And in general, I mean, this matrix just sends V, or this transformation sends V to, we have a formula for it, V dot W1, W1 plus V dot Wn, Wn. So I guess we could write this as a matrix. It's exactly this matrix, right? It should be W1. And then W1. So I'll change the W to not confuse people. Yeah, so are there any questions on that one? I think U can be D by N. The vectors are in Rn. So these should be length N. Oh, sorry. Oh yeah, you're right. I definitely did this all wrong. UU transpose is N by N. Okay, great. I was looking at U transpose U. Okay, so ignore everything I said in that part. Yeah, so UU transpose is N by N. And so the question is, when you multiply these out, then are the columns of this in W? So that's what the question's asking right here. So let's just all think about that for about 30 seconds. So here's UU transpose. And here's what it should equal. Does anyone have any ideas? Right, P should be something. Are columns of P linear combinations of columns of U? Yeah. Whatever columns these are, say P1 through Pn. This has to equal, maybe it's, V1, P1 plus Vn, Pn. Right, this has to equal something times W1 plus something times Wn. Right, this has to equal, this is an element of the column space PV. This is an element of the column space of P, but it's also an element of the column space of W, or just W, sorry. So yeah, the column space of P, yeah, both of you are correct. The columns of P are linear combinations, the columns of U, I guess you can see that in any, however you want when you multiply this out. Yeah, exactly. The column space of P is just W, right? Because P is a projection, right? So it's a linear transformation that takes a vector and maps it to this projection, right? And the column space of P, right, should just be the image of this linear transformation. So it's exactly, in the image, I mean, everything lands in W, so it exactly equals W. So everything in the column space of P is equal to W, and so the columns in particular have to be in W. They don't have to be linearly independent. No, in fact, they won't be, because P is going to have eigenvalue 0. And so P is not going to be invertible. And so its columns won't be linearly independent. Yeah. Okay. Here's an interesting thing. I'm going to go to another page. What if we were to write this? Let's see, what would the coefficients be for the W vectors in the last line? Where are we looking? What will the coefficients be for the W vectors in the last line? So here, these coefficients? Well, these coefficients have to be these coefficients. Okay, here's something interesting. What if we look at P? This is U transpose, U, I'm just gonna write out what we had last time, is W1, WD, and let's say W is inside Rn, P is the projection matrix. Okay, what if we, so this is a linear transformation. Let's say linear transformation, which sends a vector V to its orthogonal projection to W. Let's write down a matrix for this linear transformation. Write down matrix for linear transformation. In a different basis, right? We said that P is diagonalizable. Let's write down this matrix, the matrix for this linear transformation in the basis So let's take a basis of W, the column space of U, and the basis. So W1 through WD. This is a basis for W, and then we want a whole basis of Rn. So let's do a basis for the W perp. So this will be, this is for W, and let's do a basis for W perp. Let's call that something. What should we call that? We'll call that Y1 through Y R. Right, okay. So let's try to find a matrix for this. Right? What happens when if we plug in, so the way we do that, right, we need to plug in our basis vectors and write out what the output would be in our basis vectors again. So we should test it. We can probe it with like some standard basis vectors, right? This represents the vector W1, because that's our first one. And right, so what should this equal? Right, if we plug in W1 to this projection, right, you should just get back W1. So this should just equal 1, 0, 0, 0. This is represents W1, which tells us that our first column is 1, 0, 0, 0, 0. Right, and now let's probe it again. Let's do some other vectors. Let's plug in our second basis vector, 0, 1, 0, 0. This represents the vector W2, right? If we and this is the projection of W2 onto W, so we should just get, again, W2 back. This represents W2. So we should get 0, 1, 0, 0 as our second column, right? And we keep doing this. We're gonna get a D by D identity matrix here. Right, and now let's do one more, let's keep going. Now we get, let's plug in the standard basis vector, which represents our first basis vector of W perp. So this represents the vector Y1. All right, and if we were to plug that into our projection, then what do we get? Y1 maps the projection of Y1 onto W, but Y1's in W perp. So when you project onto W, you should get 0. Exactly, will the rest of the entries be 0? You should get exactly 0. So that means you get everything here is 0. Everything is 0, exactly. So this is a n minus d, n minus d. And we just diagonalized P. Right? As we should get, you know, we found all the eigenvalues and eigenvectors, 1 and 0. This is, we just diagonalized P. So in this basis, W1 through WD and Y1 through YR, this is the matrix for P. This is matrix of V maps to proj WV in the basis W1, WD, Y1 to YR. And now I guess you can ask the same question. Are all the columns in W? And yeah, this column is W1, that's in W. This column is W2, that's in W. So forth, this column is WD, that's in W. And all of these columns are 0. And 0 is always in a subspace. And so the same answer holds, that all the columns are in W. So just another way to see it. You just pick a different basis. You know, this basis, this is in the standard basis, you have UU transpose, but this is in a better basis, which is a very nice, a very easy matrix. Your projection matrix is always gonna look like this. An orthogonal projection matrix, when if you pick the right basis, is always gonna be like an identity matrix and then zeros. which is a pretty easy matrix to multiply by. Okay, we have another question. So going back to, is P diagonalizable? Which is over here. Would it also be true to say that P is diagonalizable because when you find the projection of a vector onto a span of vectors, you're basically adding the projections of a vector onto each vector in that span, and each of these projections are parallel to their corresponding vector in the span. These projections are non-interacting. Okay, I'm just kind of trying to parse exactly what was said. Okay, when you find the projection of a vector onto a span of vectors, you're basically adding the projections of that vector onto each vector in that span. Yes, exactly. That is what you're doing. When you do the projection, this projection, each term here is exactly its own projection onto W1 through Wn. And since each of those projections are parallel, what do you mean parallel? To their corresponding vector in the span. I see. So this vector is parallel to W1. That's what you say? I'm not sure what you mean by non-interacting. Maybe we can talk about this later, or you can private message me. But I think, you might have the right intuition. But in either case, if you're trying to justify it, say, on an exam or more rigorously, on a quiz or something, or just to me, a good way to say why it's diagonalizable is to say what we said before, because you have a basis of eigenvectors that span Rn. This is an eigenspace. This is an eigenspace. And together, your eigenspaces total Rn. So you have n linearly independent eigenvectors. You can take eigenvectors from this and eigenvectors from this, and they will give you Rn. Okay. Can I talk about nullity of P? Yeah, I mean, that actually just leads to the next topic, which is all this dimension of column space, null space. So we have some things here. If A is a matrix, n by n, then the dimension of column space of A plus dimension null space of A equals something. And we can do this specifically for P. Yeah, so for P equal to U transpose, or maybe you prefer the other basis, the basis which is the identity matrix 0, 0, 0. This is a block. This is called a block matrix, because I is an n by n identity matrix, or d by d identity matrix. We've said that the column space of P equals W. The null space of P, well, that should be everything that maps to 0, which is exactly W perp. And together, they add up to n, as the column space and null space should, right? Because the column space and the null space the dimension should give you n. Because free variables plus pivot variables equals total variables. Or maybe I'll say it, pivot columns plus pivot from plus free columns. What is the input basis of the initial P equals U? So this would be the standard basis on the left side. This would be standard basis, E1 to En. And this would be the basis, the diagonalizable basis, basis of eigenvectors. So W1 through WD, and then Y1 through YR, where this is a basis for W and one's a basis for W perp. Orthogonal, bases. I don't need orthogonal. So I guess I should say that this isn't actually equal to it. It's similar to this diagonal matrix. We just diagonalized it. Okay, and just filling in some of these. So another thing we notice is that the column space of a matrix plus the null space of its transpose. Well, this is actually, this may be confusing because it's an n by n matrix, but in general, these are orthogonal complements to each other. And so the dimensions of orthogonal complements have to add up to the total space. So this should be the where each, so this is a space inside Rm. And this is a space inside Rm. So it should add up to M. So it's because space and its orthogonal complement give the total space. And then if you just do the same reasoning for the transpose of A, you get each one separately. So if you apply the first one to the first reasoning in here to A transpose, then you get the third one. Nope, sorry, the fourth one. Is that correct? The row space of A plus dimension. No, okay. Can you give a quick definition of orthogonal complement? Yeah, that's everything orthogonal to your space. X is in W perp if and only if X dot W equals 0 for all W in W. So maybe in R3, for example, W could be a single line. And then your W perp would be everything orthogonal to this, which would be a two-dimensional space, right? You have everything orthogonal. Right? It'd be a two-dimensional space. This would be W perp. Can you go back to the slide with the initial presentation of U2s? Oh, this one? It's not seem to be full formula for projection. So I guess we're looking at this thing over here. Right, so this is the projection because we don't need to divide by anything, remember, because u1 dot u1 equals 1 and un dot un equals 1. All of them equal 1 because they're orthonormal. And so I think this is the projection. Mm-hmm. Okay, well, there's a lot that went on and a lot of new facts in general. Dimension of row space equals dimension of column space. Yeah, and that's because over here, yep, we have this one and this one imply that dimension of column space equals dimension of row space. Okay, so that was most of what I had planned for today. I'll be on a little while longer. You're welcome to ask questions about, any material you have, especially since the midterms tomorrow. Otherwise, good luck. And yes, I do have office hours today. I believe QR factorization wasn't even covered in lectures, so I don't think QR factorization will be on the midterm. I think that was actually in an email, maybe, I'm not sure. And the material from Thursday lecture, that was basically what I went over today. So projections and orthogonal matrices. And that could be on the midterm. You should know what an orthogonal matrix is. Thursday's lecture, yeah, was exactly what I went over today, and then review. The question is, dimension of row A always equal dimension of column space of A? Yeah, exactly. That was, these two are, this is always true for any m by n matrix. This doesn't have to be orthogonal or anything, just any m by n matrix. This is always true. And so you always get the dimension of the column space equals the dimension of the row space. Just because of combining these two. Yeah, exactly. Right. So in the first one, this first statement is true because that's a rank nullity. So that's, you have your free columns and your pivot columns, and that equals your total columns, which is n. And then here, this is because of orthogonality, right? So this is because the row space of A perp equals a null space of A. Right, anything orthogonal to the row space is in the null space, and vice versa. And that's why, this is one space is its orthogonal complement. So together they give you the full space. And then you can just, then you'll just subtract dimension null A from both sides.
Oh yeah, I see what you're saying. Yeah, I'm gonna stop the recording for now.